The next of our major theorems is understanding that if you have a domain that's a principal ideal domain, that this is automatically a unique factorization domain. So being a PID implies that you're a UFD. Now, this proof is somewhat long, somewhat detailed, and really, I don't see a huge amount of point in combing through that with a fine-tooth comb, especially because almost all mathematicians at this point in time in their life will have seen the proof of the fundamental theorem of arithmetic in great detail, and they should know and understand that proof quite well. And this is really a generalization of that in the same way that the previous slide was a generalization of Euclidean domains being PIDs. So what I'm going to do here is I'm just going to sketch through the proof, and what I'm going to do is go through and find the points of the proof that I find interesting and elaborate on those points a little bit further. So if you are looking for a more detailed, thorough proof of this theorem, it's provided for you in our textbook, and it's also very, very similar to the proof of the fundamental theorem of arithmetic. So let's start out. How does this proof go? What we start by doing is we take an element of the domain that's non-zero, non-unit, and we want to try and write it as a product of irreducible elements. So that's what we do first. We first do existence of a factorization, and we'll do the uniqueness part later as a separate thing. So for existence, let's start out with a non-zero, non-unit. If it happens to be the case that the element you picked is irreducible, then we're happy. There's its decomposition as a product of irreducibles. It's just itself. But if we're not so lucky and we chose an element that's not irreducible, let's write it as b1 times a1, where neither b1 nor a1 is a unit, or else we would have had something that was irreducible. And then let's repeat this process. Let's look at a1. If a1 is irreducible, we're happy. We've taken a and we've written it as some element times an irreducible element, and we're going to continue on until we can write it as a product of irreducibles. So if not, let's write a1 as b2 times a2, where neither b2 nor a2 is a unit. And let's continue in this way. Let's just do this over and over and over again. The thing that we need in order to have this proof that we can find an irreducible factor of a, and then we can later use this to write a as a product of irreducibles, is we need to know that eventually this is going to stop. That is, we're not just going to keep writing a sub I as b sub I plus 1 times a sub I plus 1 and never ever find an irreducible element. We need to argue that this process is going to stop eventually, and that it's going to stop in a finite number of steps. That is, we need to argue that eventually we're going to hit an a sub I in this process that is irreducible, and so we'll start by showing that a has some a sub I that's an irreducible factor. Now, what we want to do for this is we want to consider what's called the chain of ideals. The ideal generated by A, the ideal generated by A1, the ideal generated by A2, and so on and so forth. And that's going to form a chain of ideals where we have this inclusion. The ideal generated by A is contained in the ideal generated by A1. And that's because A is equal to B1 times A1. So A is certainly an element of the ideal generated by A1. If it happens to be the case that a sub I is not a unit, so a1 is not a unit, a2 is not a unit, a3 is not a unit, and so on, then it's not, what we have is a little bit stronger than just the ideal generated by A is contained in the ideal generated by A1. We have a strictly increasing chain of ideals. That is, A1 happens to be an element of the ideal generated by A1 that is not an element of the ideal generated by A. So we have a strict inclusion, as I've marked it, in this chain of ideals. So to argue that the process of selecting a sub i's that are not irreducible, right, to argue that this process eventually stops, it's enough to know that this chain eventually stabilizes. Once I find ideals, a sub I and a sub I plus 1, that happen to be equal, then a sub I and a sub I plus 1 are just off by a unit, and we have this irreducible element. That a sub I will be irreducible. Now, why I've stopped here and why I think that this is important is because it helps me introduce another concept that's super important and really cool inside of ring theory, which is when we have a commutative ring in which every strictly ascending chain of ideals eventually terminates. That is, you stop having this strictly increasing property, then there's a name for a ring that has that property, and that's called a Noetherian ring. it's Noetherian. We capitalize the N, that means it's in honor of somebody, and it's in honor of Emmy Noether, a really awesome mathematician. However, I'm going to stop at this point in the slides with being entirely mathematical, and I'm going to tell you a story because I can't stop myself, and I feel like I must say this. Emmy Noether, super awesome mathematician, gotta love, you know, rock on girl power in math. However, I was very shocked when I took my graduate course in abstract algebra to hear somebody actually bashing Emmy Noether at one point in time, and this was my thesis advisor who taught my graduate algebra course. And he was not really bashing Emmy Noether, he was just saying that this shouldn't be named after her, that she was not the first mathematician to look at rings with this property. He argued that Schur was the first mathematician that took a look at this property, and so he said, really, this should not be called Noetherian rings, they should be called Schur rings, or something along those lines that is as catchy as Noetherian. Now, however, I have to say that my advisor is a little bit biased because Schur is his mathematical grandfather. So he wants to argue that Schur is the first person who came up with this property. The rest of mathematics seems to think it was Emmy Noether who came up with this property. In either case, I'm happy. It's either my mathematical great-grandfather who came up with this property, or it's Emmy Noether, who's a really awesome woman in mathematics. But in his defense, I owe it to my thesis advisor to argue for Schur here, even though I'll be happy in either situation. I'm going to end this video with that little side note, and then we'll pick back up with real mathematics in the next slide.